Okay, great. So let's start. Um, Thanks a lot, and for everyone for joining for the Cambridge Cheminformatics meeting today. So my name is Andreas Bender. I'm here at university, Cambridge University, as well as working for AstraZeneca. So I will host the meeting today. So for those of you who joined the first time, so what is that meeting actually about? So the aim is to bring cheminformaticians together in the widest sense. So it can be anything from structure-based drug design, bioinformatics, machine learning, and both scientifically as well as personally. And so that meant for the last 10 years, we usually had physical meetings in Cambridge. So it was usually 30, 40, 50 people. And afterwards, so we had 2 talks. We went to the pub afterwards. That's a bit difficult to do right now. But now that we are online, we actually have many more people who registered. So originally it was 300 people or so who registered. It's of course fewer people turning up, but still we're able to actually cover many more countries. And it's much easier to attend this meeting, which I'm quite grateful for. And in particular, so we have, of course, many people joining from Europe, but also from Asia, Japan, Brazil, and in particular also from Iraq, Nigeria, and Panama. So I've never been to those countries. So in case you plan a Cheminformatics meeting, please let me know. Very happy to visit for presentation, for example. So what are the future dates of the meetings? So the next one, please mark that in the calendar, in your calendar, that will be on the 10th of February, and then in June again, in September. And so they will all be on Zoom next year. We might have some physical meetings here in Cambridge, but that's to be defined. It depends on the situation. But certainly those meetings which you see here, they will be on Zoom. So you're very welcome to attend or also to present if you have some work to share. You can go to this website here, c-inf.net, where you see information on the next meeting, the agenda, as well as information on how to register. And also some of you might be aware that I'm editing a Cambridge Cheminformatics newsletter. So to share information about events in the area, as well as vacancies and so on. The next one I will actually circulate quite shortly, maybe the end of this week. And so you can go to drugdiscovery.net, and that tells you how to subscribe. And in case you use that, you're also very welcome to follow me on Twitter. So then I can announce the meetings that we have, for example, or circulate other relevant information. And so this meeting, I would like to alert you to that, that will be recorded as agreed also with the speakers. And the idea is to make presentations available also across time zones or to people who cannot join due to time reasons today. And you can go to the same website, c-inf.net, to find a link for the recording shortly. I just checked for the last meeting, it's about 200 people or so who watched that recording. And so it's about the same number of people who attended our meetings. So that seems to be really worth it. And as for questions, please type your questions in the chat window also along the presentation. And then afterwards, I will look at the questions and I would like to ask you to unmute yourself and to ask your question orally so that there's some kind of dialogue as well. And feel free for the speakers, as well as if you ask a question, feel free to switch on your camera if you feel comfortable so that we have some more or less personal interaction here as well. And afterwards, so we will have talks, as I said, for our Cheminformatics meetings. Usually we went to the pub afterwards, difficult here. But if you feel inclined, feel free to put your beer into the fridge or to prepare coffee or whatever you prefer. Because after the presentations, we will have a pub night to meet your fellow cheminformaticians. So to meet people you know already or people you don't know yet. And so we will do that here in Zoom. So we will have breakout rooms, assign 6-8 people or so per breakout room. And I will merge clusters, so to speak, because not everyone will stay on quite likely, but I will put people together so no one feels alone afterwards. And so please do stay on after the presentations as well. And if you wish to present at the next meetings or have any other information to circulate, please let me know. So I'm very happy to include that in the newsletter that we have, as well as to include your talk into the agenda for one of the next times. Please just let me know. Thank you. So what's on the program today? So we will have 2 presentations. The first one will be assessing the frontier, active learning, model accuracy, and multi-objective candidate discovery and optimization by Zachary del Rosario from Olin College. And afterwards, the second presentation will be on molecular similarity search using Elasticsearch by Konstantin Perikov from EPAM. And afterwards, we will have our social pub night. So let's start with the first talk, and that's a presentation that is very close to my heart and interest as well. And so that's a presentation or publication I came across maybe 2 months ago, something I advertised in our Cheminformatics newsletter as well. That's a very important topic, how you validate models. Can you do that retrospectively? Well, not really, because in this case, you sample from similar distributions, you can only rediscover what you know already, right? And so that is difficult to do with cross-validation and so on. You're only trying to simulate a process of future discovery. On the other hand, if you do a prospective validation, it's limited. The sample sizes you can achieve are limited if you need to do some experimental testing. And of course, tests are always biased as well. And how do you compare to baseline control, so to state of the art? And there was an article from a person at Google recently, and you might have seen that on my blog. Every model validation is actually process validation, right? You never validate a model by itself. You pick new compounds, which you test, but those compounds, which compounds you choose depends on availability, for example, right? So model validation is always process validation. It's difficult to validate a model, basically. But in this article that Zachary presented, there were actually very nice new ideas. And so I'm very happy that he's here today to present. And that's the presentation we would like to start with. So we'll start with assessing the frontier. Zachary, if you don't mind, could you share your screen?
Sure thing. Thanks, Andreas.
I will just share. Okay, I will just stop sharing. Okay, now you should be able to share your screen.
Great. Can people see my slides here? Awesome. Thank you. All right. Thank you for that nice introduction, Andreas. As he mentioned, I'm Zachary del Rosario. I'm a visiting professor over at Olin College. And today I'm going to tell you about our work on assessing the model frontier. And what I'm going to suggest is a more science-driven problem framing. I believe that we've inherited some ideas from the machine learning community that really deserve a little bit of a critical look at. So that's really what this talk is going to be about. Now, as far as who are the people involved in this project, it's a joint effort between a couple of groups of people. My colleagues and collaborators come primarily from Cheminformatics. Citrine is a software company who provides a data and AI platform to help companies develop novel materials faster. So they have a pretty vested interest in figuring out the truth or the underlying mechanisms behind using machine learning for things like materials discovery. As for myself, I'm both a graduate of and a visiting professor at Olin College. So Olin is a really quirky, small engineering school outside Boston. We have, at any time, about 330 undergraduate students total, so we're very, very small. And we're really a test bed or a laboratory for testing out new ideas in engineering education, very much focused on the development of pedagogy. So here's what I'm going to talk about today. I'm going to start with some motivation. I'm then going to dig into multi-objective active learning. That is the topic of the case study that Andreas highlighted in the paper that he referenced before. I'm then going to make a brief comment of what I think is a little bit more of a science-driven problem framing within this whole context. And then I'll end with some concluding thoughts. So to start, what's the motivation behind this kind of work? Well, the motivation is really towards accelerated discovery. Often, in the kinds of problems that we in cheminformatics or materials informatics have, we have a massive search space, but we have very sparse data. So for instance, in picking from this particular review paper that I have cited below, there are a number of different case studies out there that give us very sobering big numbers. So one case study looking at a search space of 1.6 million organic LEDs, another looking at 4.6 billion different high entropy alloys, and yet another case study looking at over 8 billion possible layered semiconductors that we could go produce, but we have quite a bit less data to get started in that kind of space. So for instance, this visual helps make the problem a little bit more clear. Here, what I'm showing you are some reduced dimensionality coordinates, TS and E to be precise, and we're looking at a data set of high entropy alloys. So the problem we have is the following. We have some small amount of available data. So these explored points are points where we have experimentally synthesized and characterized some materials. And so we have some information within some of these various clusters. But if we take a look at the entire search space, or really even just a fraction of the search space, there are these islands that are quite a bit far from where we have data. And so if we were to try to make any predictions out here, we might be sort of fumbling in the dark. Our materials intuition may not actually generalize out there. So an idea is to use machine learning to try to guide some of this process. So to try to make predictions and guide discovery within this space. Now, I will go ahead and out myself right now. I am not a cheminformatics person. I'm coming more from the material science community. My colleagues and I work to develop novel structural and functional materials, but a lot of the same concepts apply to things like drug discovery. The primary message that I have for today is that off-the-shelf measures of model accuracy can be actively misleading when what we are actually trying to do is seek novel performant candidates. This is the kind of thing that we've seen personally when it comes to materials development. The same kinds of lessons, I believe, apply to things like drug discovery. And I'd imagine any case where you're applying the same kind of approach, this using machine learning to guide discovery, the same kinds of lessons are likely to apply. So what do I mean by this actively misleading idea? Let's take a look at some example results. Now, I haven't told you everything that you need yet to fully understand this plot, but let's go through this roughly to start. So what I'm showing you here is on the vertical axis, mean non-dimensional error, a measure of model accuracy, where lower is better. And on the horizontal axis, I am showing you iterations of active learning. So what we're doing here, in essence, is we are starting with some sort of initial data set. We are training a machine learning model, using it to make predictions, using that model to decide which data to go collect and add to our test set. And then we are retraining the model. And what we can see is that different approaches, different computational pipelines lead us along different trajectories in terms of how this model error evolves. Now what we're seeing here is that this dotted line here corresponding to MPJE, an approach that I'll describe a little bit more in detail later, we see here that this approach is getting us to lower error faster. So at first blush, it seems like this might be a preferable way to carry out our computational process. But what we can see is that the most accurate approach here is actually giving us the fewest improved candidates. This right-hand plot is showing you the number of acquired frontier points, so top performing candidates within a known data set. We're seeing that the approach that's giving us the lowest error is actually giving us the fewest improvements in terms of the actual scientific outcomes, the discoveries that we want to get to. So this is what I mean by actively misleading. If we were to choose our computational pipeline based solely on this metric, we wouldn't actually be getting at the scientific questions we're trying to answer. So this leads us into the case study that I'm going to talk about. I'm going to be drawing on some work we did in this paper, Assessing the Frontier, and this was a case study in multi-objective active learning. So what is multi-objective active learning? There's a lot of ideas baked into this big polysyllabic string. So let's pick apart each of them piece by piece. So first of all, active learning, in the sense that I'm going to use the term, is the following. We're going to start with some data set. We're going to then fit a model to that data set. We're going to use that model to choose candidates. Say I were trying to optimize this output quantity. Well, I might pick a candidate over here. I'm going to go now experimentally synthesize and characterize that candidate. And I may find this candidate, it's not actually an improvement over what I've seen before. So what I'm going to do is I'm going to add that candidate now to my data set. I'm going to then repeat this entire process. So I may fit a new model to these data. I'll make another prediction, and then I will go synthesize and characterize this point. And in this case, I happen to win. So I happen to find a candidate that is an improvement over what I knew before. And so this would be a successful application of active learning for something like candidate discovery. Now, when it comes to doing optimization with a single objective, it's quite straightforward to make a pick about which candidate we should go and actually try next. But when we're in a multi-objective setting, the situation is more complicated. So in a single objective case, we can line up all of our different points, and we can simply pick the greatest objective value and say, aha, that's what we should go with next. But in the multi-objective setting, things are a little bit more complex. We don't just have the setting where we have greater and lesser candidates. there is an entire other option for us, which is for candidates to be non-dominated, for another instance to have a greater objective value along one axis, but a lesser one along another. What this means is we no longer have some single global objective value, but we instead have an entire frontier of possible best candidates. Now, one of the complications this introduces is now we need to make some kind of decision. We may have some frontier of possible candidates that we could go select. So there are some degrees of freedom in how we set up our decision logic. So one of the things that we were testing in this assessing the frontier case study was the geometric fidelity with which one represents the Pareto frontier. So for instance, over here on the far right, I'm looking at a fully accurate representation of the Pareto frontier, what I'm going to call MPND, maximum probability non-dominated. This is exactly representing the Pareto frontier geometrically speaking and carrying out a probability integration. We could imagine going towards a lower fidelity model for the Pareto frontier. So for instance, this hyperplane improvement approach is just fitting a hyperplane to our existing Pareto frontier. And this joint exceedance approach is really just taking maxima over all of our different observed objectives and really giving us this box, well, hyperbox in higher dimensions. The very precise details about this side of the case study are not terribly important. What I really want to highlight here is that one of the things we were setting out to assess are basically design decisions and how we set up our entire data pipeline or decision pipeline, really. So we were looking to assess what choice should one make when it comes to setting up this kind of active learning pipeline. And there are various ways we could actually carry out that kind of assessment, either in terms of things like the model error, the model accuracy that we observe when we choose, say, MPJE versus MPND, or we could look at things in terms of, well, how many candidates are we actually returning? So here is a summary of that entire workflow within the multi-objective active learning setting. Just as a reminder, we obtain a data set, build and assess a model, use the model to suggest candidates, then synthesize and characterize, and then we check if our new candidates meet our criteria, we should probably stop. If not, then we can continue the process from step 2. Now, there's a lot going on inside this whole process. So what I really want to zoom in on is just the building and really the assessing of the model. This is the piece of this whole pipeline that I really want to focus on. So there's quite a bit that's known about things like model assessment, at least when it comes to quantifying model behavior in terms of error. For instance, one thing that's very broadly known is that training error is a very optimistic, biased notion of model accuracy. And this should make some intuitive sense, because if we are using data to train a model, we are doing our best job of fitting that model such that it minimizes error on those data. And so it's sensible that since we've worked really hard to minimize error on that data set, we're going to get a very rosy picture if we quantify accuracy using those data. So something that's equally broadly known is that it's better to actually quantify model performance using something like test error. So in this case, what we do is we train a model on some subset of the data, call it the training data. We hold out another subset, let's call it the test data. And we train on one set and test and compute accuracy on another held out set. And this other measure is going to be a less biased measure of model accuracy. Now, often when we do this kind of test train split, we assume some kind of random sampling. And that's coming from some intuition from statistical learning. But the thing I want to highlight is that usually when we are using active learning for pushing the frontier of known candidates, we're usually not just guessing randomly. We're usually fairly biased in terms of where we are selecting candidates. So when we're trying to get top performing candidates, we're going to tend to be using the model in more of an extrapolation mode rather than just sampling from some sort of representative distribution, or rather than just thinking in terms of some sort of representative sample. Putting this differently, statistical learning is really about average performance. But when we're using active learning in this setting, we really don't want average candidates. And as we've seen before, something like average error can actually be misleading. So we saw earlier this figure where we saw that using this MPJE approach within our whole decision pipeline tended to push us towards lower error more quickly. But with this other viewpoint, we can see that this same approach, this MPJE approach, tended to give us the fewest improved candidates. So here's an idea. Could we start to fix up this idea of model accuracy? So one idea we introduce and explore in this work is that what if we try computing accuracy with respect to some different scope? Say we select not just the average error over the entire data set or over our entire domain. Let's instead think about, can we target only those candidates that seem to be relevant to the kinds of decisions that we're making? So here's the way we're going to get at that. I introduced this idea of a Pareto frontier earlier, this set of non-dominated points. We can recursively apply that definition. So imagine I take a data set, I find its Pareto frontier, I'm showing that here in red. I then remove that Pareto frontier from the data set and I recompute the Pareto frontier on the remaining data. That gives me now this green set of points, and I can recursively apply this idea. These different bands are known in the database literature as strata. What I could then do is I could use these strata to define some new subset of the data where I can go and compute my error. So for instance, taking the first two strata would be what we call the Pareto 2 shell. This feels like it'll be more closely associated with the kind of model performance that we actually care about, since this is more closely aligned with where we're going to be picking candidates. So here's a hypothesis that we can go and test. Shell error will tend to correctly rank active learning procedures in terms of their candidate acquisition performance. This is something that we can go and actually test experimentally and see if this bears out in practice. And so it turns out that shell error can be more informative. So let's take a look at one instance where that is the case. What I'm showing you now is another of these performance plots. So we're seeing here model accuracy on the vertical, active learning iterations going forward on the horizontal. But now I am splitting out measures of accuracy based on global, so computing over the entire data set, versus 3 shell. So using this slice idea of taking points close to the frontier in terms of highest performance. What we can see is that over here, our 3 shell error is giving us the intimation that, sorry, I'm getting myself turned around here. The global error is suggesting to us that this MPJE approach is going to be the highest performing model. But if we take a look at 3 shell error, we see a different picture where it seems as though this MPND approach is actually going to be the most performant. And if we take a look at results in terms of actual acquired candidates, best performing candidates, we see that indeed the rank ordering over here, so MPND lowest, followed by this dashed line MHPI, followed by the dotted line MPJE, follows the rank ordering with MPND at the top and MPJE more in a middling sort of position. So this is promising. It seems like the shell error might actually be able to correctly rank order these kinds of approaches. But I want to point out that this notion of shell error is also not guaranteed to be more informative. So let's take a look at a counter example. Here we're looking at a data set, QM9. It's a computational small molecule data set. What we're seeing here is that in terms of 1 shell error, the best performing approach seems to be this MPJE approach. But if we take a look at things in terms of acquired frontier points, we're seeing that it's actually somewhat middling in terms of discovery of candidates. And what's actually top is this MHPI approach. And if we take a look at one more instance, another data set now, a circular, a synthetic benchmark data set, we can see that if we quantify error in terms of 3 shell, we see that all of these are roughly similar in terms of their actual accuracy performance. But if we take a look at how they're performing in terms of acquiring new candidates, they're actually quite well separated. So here we have very little signal in terms of how to order these different approaches in terms of error, even shell error, but we could see in terms of the number of candidates that they're able to produce, they're able to identify, they're actually quite well separated. So at this point, I think it's natural to wonder, well, gosh, we tried to fix up this error notion. Well, maybe there's some other factors that matter underlying these kinds of problems. Maybe things like the inherent difficulty of learning the response might be at play, or maybe the smoothness or regularity of the underlying response might be important. But there's something I want to really zoom back and take a look at more. Remember, the message that I was trying to leave with is that these off-the-shelf measures of model accuracy can be actively misleading when seeking novel performant candidates. And what I'm introducing here, this different idea of really, let's look at a different kind of model error. It's really trying to fix up or patch up this idea of model performance as quantified by accuracy. But what we're seeing is that it's still not really the full picture. What we're seeing is that accuracy, be it global or say this Pareto shell notion, it's really just a weak predictor in this kind of scenario. And the thing I want to take a step back and look at and sort of zoom out a bit more to discuss is that really, I think the dominant ideas or the dominant paradigm in machine learning is really encouraging us to focus on some potentially irrelevant metrics when it comes to the kinds of science questions that we might actually be trying to answer. So here's a proposal. Let's try to keep in mind a more science-driven problem framing as we're applying these kinds of techniques. So I want to go back to the ideas of active learning as they were originally conceived within more of the machine learning community. So more within its original birthplace. So here I'm pulling some quotes from a literature review on active learning by Burr Settles. And here he writes, in this way, the active learner aims to achieve high accuracy using as few labeled instances as possible, thereby minimizing the cost of obtaining labeled data. Where active learning as a business really came from originally was from a problem setting where folks in machine learning wanted to train a model, but didn't have access to all that much data, and wanted an intelligent way to select which data should we go and obtain in order to train as accurate a machine learning model as possible. So this focus on accuracy is really baked into the original conception of how active learning works. What is our objective when we're applying these kinds of approaches? But to bring things back to what we talked about before, statistical learning, so the framework or the theory that we often use for quantifying machine learning accuracy is really about average performance. But at least when we're using active learning to discover top candidates, that's really not what we want. We don't want average candidates. We're usually going to be using our models in more of an extrapolation scenario. And I think there's a really fair question to come back at me with right now, which is, Zach, isn't this obvious? And I would say yes. I would say some of these ideas, a lot of these ideas are fairly obvious, which is why I still find it so disturbing to see accuracy over things like to see obsession over accuracy metrics like, say, root mean squared error or R squared or these other sorts of things. And I think it also creeps into the way we set up our computation or data science pipelines for going forward and deploying these kinds of things in practice. So often when we are setting up some kind of pipeline, we're going to be making decisions about, say, how we set up the model, how we set up our decision logic, based on things like model accuracy, say k-folds cross-validation as an error for doing model, as an error metric for model selection, or really an estimation procedure for model selection. And what we're seeing here is that if accuracy is only a weak predictor of the thing that we're actually trying to accomplish, which is to find top performing candidates, that might actually bias our model selection in a direction away for what would tend to get us the kinds of scientific payoffs that we're really seeking. So one solution to this, and admittedly it's a partial solution, as Andreas was alluding to earlier, is actually doing simulated active learning when it comes to making decisions about how to design your pipeline. It's a more expensive way to assess whether or not your entire process is actually to make decisions within designing your process. But I argue that when you're looking for, say, improved candidates, that's really the thing that one should be assessing. So bringing this back to the broad level, I think where this matters is in how we frame the problem. So I think it's useful to have some terms just to describe what it is we're doing. I'm not married to these terms, but I want to draw a distinction between model improvement as an objective, where we are designing algorithms so as to improve model accuracy. That's the original conception behind active learning. Sometimes that's what we're genuinely trying to accomplish. Sometimes we really do want the most accurate model that we can build. But in other cases, what we're actually looking for is candidate improvement. So in this instance, we are designing algorithms so as to choose the best candidates possible to make the most impactful scientific discoveries that we can. And where this really matters is where it comes down to making decisions. Because what we can see here is that if what we're doing is trying to best improve our model, well then what we would tend to select, at least within this particular instance, is this MPJE approach, which is getting us to lowest error faster. But if what we're actually doing is candidate improvement, well then we would make a different selection. And furthermore, we couldn't make that selection unless we were actually quantifying our model performance in terms of the metrics that we actually care about. So in closing, off-the-shelf measures of model accuracy can be actively misleading when what we're really trying to do is seek novel performant candidates. Accuracy is really only a weak predictor, at least in the instances that my colleagues and I have seen. And so the thing that I encourage you to think about when applying these kinds of techniques is really to think about whether you're doing model or candidate improvement. No one of these problem framings is objectively better. It really comes down to what problems you are actually trying to solve. So I want to end with some pointers towards other further reading that I think are useful. I was drawing from this Assessing the Frontier paper that my colleagues and I published a little bit earlier this year. As Andreas mentioned earlier, he wrote this really nice article, which I think actually zooms out and looks at even more of the factors that are important here when it comes to how you set up an entire process for doing things like supporting scientific discovery using these kinds of machine learning data science techniques. And I will note that when it comes to this idea of candidate improvement, really Bayesian optimization is one place where there actually is some theoretical grounding behind going and doing that kind of work. So that's a search term, if you're not already familiar with, that you can go and look into. That's all I've got. So at this point, I'd be happy to take any questions.
Great, thanks a lot for your presentation. Excellent. Let's start with Raj. Raj, do you have a mic? Would you like to ask a question?
Yes, thanks. So the way you define the shell error, wouldn't that tend to be over-optimistic?
Can you explain what exactly you mean by that?
So in the plot that you showed in the model accuracy, I think that was the plot, you showed that using the shell error, it identified a method that had much better accuracy. And in the corresponding plot where you showed the best candidate, that matched up. But then in the counter example, I think they flipped again. So right here. So in this case, the shell accuracy correctly identifies the method that gives you the best set of candidates, but that didn't seem to hold in the counter example where the shell error doesn't identify the.
Yeah, so Rajesh, what I'm trying to make a point of is that this idea of shell error, so first of all, global error, and even the shell error, which we have attempted to tune for being relevant for this kind of setting, is not really giving us all that much useful signal. So this is, to be totally upfront, a negative result, scientifically speaking. I am not claiming that shell error has magically solved our problems. What I'm really trying to say is that the idea of using accuracy to assess something different, which is how many candidates are we discovering using this kind of computational pipeline, those things are at best weakly connected.
Got it. Thank you.
Yeah, thanks, Raj. And Philip Seidel, yeah, he mentions there was a similar paper apparently recently. Philip, would you mind mentioning that paper, describing it?
Well, yeah, it's not completely similar. I mean, they talked about a lot of things in this paper, but it's this paper on the specification in machine learning. And it's about from those, I don't know, few hundred Google employees. But they also talked about this problem about model selection. So when we then employ the model and we select the model by having the best performance, this might not be then the best performing model in production. And they also looked at it through via training. I have it open here. It's figure 3 in this paper. So the point here is that they make is one would have to have a separate set, an out of the main set, quote unquote, and evaluate on that. And that might give you a bit better decision making about which model to choose then. But yeah, it's not really a question, but more of a bring together those two things.
Yeah, sure. Feel free to post the link here if you have the link to the paper, because that might be interesting for other people as well. Feel free to post it here in the chat. Yeah, great. Thanks.
Yeah, thanks for that, Philip.
Yeah, thank you. Yeah, Konstantin has a comment as well. I'm not quite sure. It doesn't seem like a question, right, Konstantin? Or would you like to elaborate on that?
Sorry, yeah, it's rather like just double checking that my understanding is correct, right? Because traditionally in the machine learning, while we're using this accuracy, like the error, the metric, it's because, we want to tune our models to make it, more correct one. While in the, let's say, drug design or materials design, we rather want more candidates. We're not sure about like trying to find just, less error or something. So I was just double checking that my understanding is right here.
Absolutely right, Konstantin. Spot on.
Yeah, that's right. And Bipin Singh has a comment regarding interpretability. Bipin, would you mind saying that? Yeah, I'm not quite sure. People might not have a microphone. But his question is regarding, there are methods for explaining machine learning model interpretability, how this approach is different from those. The way I understand it, it's a different aspect, basically. But are there any interpretability aspects that you can mention or want to mention?
I have not gone and tried to compare head-to-head things like model interpretability metrics and things like candidate performance. That could potentially be an interesting thing to look into. The point that I was trying to make here is somewhat different in nature, which is when what we care about is actually finding better candidates. Well, it's one of these observations that's kind of so obvious it feels dumb to say out loud. But when what we actually care about is improved candidates, well, we should probably quantify goodness in terms of number of improved candidates. But then you could start to draw that idea backwards and say, well, if what we actually care about is improved candidates, maybe that's the metric we should be using for, say, things like model selection or process design, that entire, all of the stages along here that feed into how we set up our entire, say, drug discovery pipeline.
Yeah, that's right. Christos Nicolaou, either, do you have a mic?
Yeah, I do have a mic. Thanks for the talk. This is really interesting. Just wondering, we're spending a lot of time on reliability assessment, applicability domain, and I guess what always comes to mind when I hear these kind of talks and read these kind of papers is that not all models are created equal, right? There's models and models, and in some cases, the criterion or the goal of getting the best candidate outs may not be what you're after, right? What you may want to do is design libraries that are going to set you up for success in a subsequent step. You recognize that you don't know enough to design good molecules early on. So an absolute measure of how many good candidates you get may be premature, I guess. So I'm just a comment, right? It does depend on the stage of investigations that you are, the availability of data that you have, and really your goal can fluctuate depending on that.
Oh, I agree 100%. And I can imagine there are some cases where model improvement is really the thing that we want. If we're going to be making a whole bunch of draws that are similar to what we saw in the training sets, well, then that is a that seems to me like a fairly sensible way to actually quantify model performance. Christos, I'm not trying to argue that, say, my problem framing is the one true problem framing. So I would agree 100% that whatever it is that you are actually trying to accomplish, it really comes back to designing the metric or the way to quantify performance that's best suited to that particular problem framing that is important, rather than, say, importing these ideas from machine learning, things like this obsession with model accuracy. That's the thing I'm trying to question is, well, when is that an appropriate way to actually assess the model? And what is it not so appropriate? When is it not really connected with our scientific goals?
Yeah. Great, well said.
Yeah, that's right. It's because I was also mentally trying to transform or translate that to the drug discovery field. Yeah, you have quite a number of endpoints, some of which are for biological endpoint models. Yeah, that are only proxy models. They are very crude models. Sometimes you don't want maxima or minima. Yeah, it's good to have a range in the middle that is appropriate. Yeah, I was also trying to translate that. And what Christos is saying, yeah, the models are still crude. Yeah, that's true. I mean, it's proxy endpoints. Yeah, we have some applicability to in the chemical space. Yeah, what does the endpoint of the model mean for the biological case? There are a few steps basically how to translate that to the drug discovery space. But the point you're making, Zach, I fully agree with that. Accuracy is maybe not the right thing in every case. That's right. So I was trying to translate it to that space as well. Yeah. And that's good. Let's do one more question, then I think we need to conclude this part. Richard, do you have a microphone?
Yeah, no, thanks. So firstly, I'd like to thank the speaker for a really fascinating talk, and I definitely need to read the paper to fully understand everything. My first impression, however, is that I'm wondering how well it's meaningfully possible to characterize, if I've understood correctly, that, you know, talking about that being the objective, the ability to discover the future, you know, which compounds are going that we haven't seen before, for example, that are going to be most important to make it in the future. So whereas, for example, in statistical learning theory, cross-validate, there's a theoretical basis for believing that, if your cross-validation should at least be able to tell you how well your model can perform for compounds inside the domain if you're sampling from the same distribution. And in principle, you can estimate whether or not new compounds are from that same distribution or not. So in principle, your ability to make those predictions, if you determine that they are from the same distribution, is characterizable. However, I'm wondering how well you can argue that, and you can characterize your ability to discover unknown things is. So I think Andreas had a good analogy in his How to Lie article, which you've referenced here, which is that, so for example, 2019 was arguably a lot more predictable from 2018 or 2017 than going from 2019 to 2020. Is there some issue there, or am I missing something?
Richard, you're raising a very good question, and I think I'm highly, highly tempted to just punt and say go read Andreas's article, because I think he addresses that a lot more comprehensively than I do. I will say I am not yet sure to what extent we can actually say how predictable, because things like when we're running these kinds of retrospective active learning, simulated active learning procedures, it's encouraging to see that, say, one approach performed better within this simulated setting, but you're absolutely right that this is in no way indicative of the kind of performance that we're actually going to see. So when it comes to things like numerical differences between these different approaches, you're right. I wouldn't be willing to stake money on saying, well, numerically, this is going to say get me 3 or 4 more candidates on average than, say, another approach. My gut feeling is that this will at least get us more in the right direction towards building up pipelines that are more likely to get us better discoveries in practice, but I don't actually have any guarantees on that. And I'm personally not familiar with any theory that really gets at that aspect of the problem. If anyone knows of anything like with a theoretical grounding that actually lays that out. I mean, Bayesian optimization gets at some of that, but I don't know that it really starts to address the kinds of questions that we have. So Richard, unfortunately, I'm gonna have to throw my hands up and say, I don't know.
No, thanks very much. I agree. It's a very interesting problem, and I agree that the focus upon that you've introduced here is something I think we all need to think about. So thank you.
Thank you for the question.
Great, thanks a lot, Richard, for your question. And thanks a lot to the speaker again. Thank you for your contribution. I think that's a really important topic, to be honest. Thanks for joining us today. Excellent. We'll move on to the next presentation then by Konstantin Perikov. And so that's about similarity searching. It's more or less bread and butter in the cheminformatics field. But what's happening is, of course, the libraries are getting bigger. We know of the enamine library, virtual libraries. So sometimes you have 1 billion molecules, let's say, or something on that order of magnitude. So the question is, how can we search that efficiently? And this is what Konstantin was working on. Konstantin. Oh, yeah. You feel free to share a screen and yeah.
Is it sharing now?
Not yet.
Oh, sorry, I didn't click the share button.
Yeah, no, sir.
Should be good. So yeah, thanks for the introduction. Yes, I agree. This is very important subject at the moment with the libraries or databases growing up, and we have more and more molecules. So yeah, so today we're going to talk about how we're going to do a molecular similarity match using Elasticsearch and how we could do this efficiently. And to be honest, this will be a blend of theoretical thing, but let's say it's more practical approach since So since I'm mostly an engineer, I'm not some sort of PhD or have a science degree, rather than like, general master something. So yeah, I'm Konstantin Perikov. I'm a chief software engineer at EPAM. What I'm usually do, like in my day job, I'm doing search information retrieval system for different types of domains, like patents, publishing, like articles. And recently, to be honest, like maybe last half a year or so, I'm really got fascinated by cheminformatics and the information retrieval problems in this domain. So this is why I naturally got into the similarity match problem. And yeah, this is once again just to make sure that it's not that this is talk about, but my knowledge is still growing. So I initially want to ask, if I misuse some terms, so it's really a start for me. So what we're going to take a look today, we're going to take a look very briefly for the molecule ways of representation. And I know for quite a lot of people here, it's a very common topic. So I will try to make it very fast. Then we're going to take a look of the chemical similarity, once again, very fast. And then we're going to spend the most of the time on what we did based on the Elasticsearch and how we could use it. And at the end, we could potentially have some sort of comparison with others open source framework which exist in this field. So once again, a very brief one on the molecular representation. I'm pretty much sure it's well known to all of you. When we're talking about some of the compounds, they could be presented as molecule formula, for example, like this, or some names. I think this is pretty much clear. The problem, of course, is that those are not that well enough, and then you're looking at the structural formulas. So for example, like this, once again, for caffeine. And this is, of course, a graph representation, and they could be much more complicated. And then, of course, we have even more ways to represent the molecules and compounds. We have smiles, which are a depth-first search on the graph representation. We have INCHI, we have mol files, which are having the coordinates and bonds and stuff like this. And you could see that we already have quite a lot of formats. And I didn't even touch like SDF formats and the others that exist. So of course, it's very important for a proper API which would work with different formats and work with them efficiently. So this is something we take a look ourselves during the development of this kind of stuff. And of course, the similarity match. And when I'm saying similarity matches, of course, I'm rather meaning like this, like let's say the three subsets of the problem. So similarity match as of finding similar compounds, as of substructure match when we're finding the compounds which are having subset of the molecule, and then of course of exact match as well, which is just finding the exact same molecule in the database. And of course, this is important in drug design, especially when we're talking about ligand-based design. When we're looking for potentially candidates which are looking pretty close to the existing compounds or molecules that we're working on. And yeah, of course, some interesting reading, at least first for me, a very, very interesting one as well. So yeah, and once again, for those maybe who missed it a little bit, it's very complicated, and this is why searching similar molecules could be sometimes tough, is that for the moment, the example, we're looking at exactly the same molecules here. It's a caffeine, but it just, rotated, so it's different smiles representation, as you could see, and different graphical representation. And if you could think of searching this efficiently, it's very difficult to do in a normal, let's say, information-driven textual way. So that's why there is like different approaches how to do this efficiently. And with, let's say, substructure match, when you have addition of some sort of functional group, like in this case, HAHO, once again, smiles are different, very difficult to do in a traditional full text search way. And as I promised, I was just very, very quick on these initial things, assuming once again, it's bread and butter for most of the people on this meeting, so it's clear and understandable. So now I'll slow down a little bit and think what we are trying to do. So when we looked at the different tool sets which exist in this field, what we saw is, most of the time they either focus on traditional relational databases such as Postgres, SQL, or Microsoft, or MS SQL or something like this. We didn't have a look, and we didn't saw much of the, let's say, traction using full text search engine such as Elasticsearch or similar to ones built on top of inverted indexes. So we take a look here and think, hey, we could do something which would have a nice API in order for us to load the data into Elasticsearch, search this efficiently, find similar molecules, find substructure molecules or exact match, and this we could do this efficiently into Elastic. Why we choose the Elasticsearch? In information retrieval field, to be honest, this is a pretty standard de facto tool at the moment, because in most of the cases, if you're using this for, let's say, searching a patents document, patents database, in most of the cases, it will be backed by something built on top of Apache Lucene Java library. And Elasticsearch is one of them. Let's say another one is Apache Solr, which is quite common. You could call them siblings in a sense. And of course, in recent years, let's say maybe last 5 or 7 years, something like this, Elasticsearch gets grown very, very big popularity. Another aspect which we like a lot, and as Andreas mentioned earlier, the databases of compounds are growing pretty much extensively, and we have more and more data. And when we look into how do you actually going to search through this one, you're expecting that the storage, let's say, your NoSQL or relational database should have an ability to scale horizontally. For example, in order to incorporate more and more data and search this efficiently. So instead of having just one big server, you would rather separate this into different nodes, let's say in a cluster and something like this. And in this case, Elasticsearch once again working just flawlessly because of this cloud native nature. So what we did, let's take a look at some sort of diagram explaining architecture of an API that we built. So the idea is pretty straightforward, is that we have some sort of certain storage which contains different types of formats like mol files, SDF files, smiles files, and others potentially. You read those compounds, for example, using our API in this case. So this is already happening with our API. Then you could create actual, records like compounds incorporating those data. You could enrich those data. And here we're talking potentially about different pluggable fingerprints, because there is, of course, many types of it, or enriching it with different, let's say, maybe bioactivity data, or other, let's say, tags or labels or something like this. So you could expect to have it and to have it to be enriched. And this is, of course, very important to later use this kind of record or document. And when you put it into Elasticsearch, you have an ability to search this efficiently, first of all, from the chemical compounds perspective, but also have ability of this extra filtering, let's say, maybe finding the tags that you associate it with. At least I was thinking of example that maybe in a big organization, you maybe have a potential different like labs or sub-labs, let's say, working on different compounds. And then instead of scanning the whole database, you would rather filter out by some of the tags, or filtering out it by some sort of range of bioactivity data. So for example, you might have data for these possible compounds associated with certain targets and special metrics. Filtering out by this would be also beneficial. And Elasticsearch with this full text nature, it should be very, very important and should be very, very efficient. So what we did here is we built two sets of API at the moment. And this is a fully open source version. I just provided some of the links and I will send you afterwards as well. So we built two of them, which is one is based on Java, using quite heavily the Stream API there. And on the other one, we're using the Python version because I think we're understanding how crucial the Python support is for the scientists especially. So we're using the quite recent version here as well, just to support several nice features like type hints and data classes potentially. Unfortunately, this is something which I was having a small chat with Andreas before. We're still working on this making available in the like Maven Central and PyPy, so it should be available pretty soon for you to use. But that's a little bit in progress. So I hope it will be completed pretty much soon. Another from the practical thing, of course, for those who maybe not that much aware, we're trying to use the Stream API in Java version of this API, and this is basically creating a sequence of elements and supporting some sort of sequential operation. So you could think of it as we created the stream saying, hey, I want to get my stream of molecules backed by Elasticsearch, an Elastic repository in our case. Then you could do some sort of intermediate operations. For example, you could filter out by similarity match, asking, hey, I want only to find the molecules which have Tanimoto similarity of the certain thresholds. Then you could filter it by additional properties, which we were talking about earlier, like enriching stuff. And then you have a terminal operations, which is basically making a request to the storage in our case. And streams are lazy by nature, so constructing them should be very efficient. It's only executing when you collecting them. So how we do the match? So basically, the question is, right. And I must say that this work is heavily inspired by, let's say, some of the work which was done like maybe a couple of years ago, 2 or 3 years ago, I think. Because the idea of putting something into like something like Solr was standing around for a while, but I think we tried to work on top of this this experience and try to go further. So it's like a look at some of the difference, which are, I think, very important. But from the logical perspective, when we're looking at the compounds, of course, before I was talking how complicated the graph structure is, and of course for the databases like relational databases or NoSQL databases, it's very difficult to understand the notion of the graph. You could think of some of the graph databases, let's say, but they on the other side wouldn't be able to do this kind of similarity matches pretty efficiently. So what we try to do, and here I'm illustrated a very simple example, is that for several compounds we created a certain of fingerprints, and of course, they could be very different types of fingerprints. How they would be stored then internally into Elasticsearch. And I think for the Elasticsearch, the main idea of it is having an inverted index. And in this case, the efficient structure would be, which is called sometimes a posting list. And it's working like this, basically. You remember that before we were having, for each of the compounds, a number of bits in the fingerprints. And once again, I probably move this too fast, but like fingerprints is a standard way of representing the compounds, especially for the match problems like this. They are like extension of what was initially like structural keys. But an idea is that, let's say for bit number 1, we have a very efficient structure just saying, hey, my compound 1 and 2 is actually having those bits. Then for bit number 2, you have only compound 2 in our example, and so forth and so forth. And basically, later, when you need to do this kind of operation, you could do this very efficiently working on those bits and bits intersections. So yeah, let's take a look how the exact match, for example, should work in our case. So we're going to have a query molecule basically, and its fingerprint representation. What it means basically that we would need to have a intersection of all those bits and finding those. And if returning back to the previous one, this is as easy as just finding several bit sets and just intersecting them. And intersection is blazing fast. It's very efficient operation. It's just reducing documents in a very, very, very efficient manner once again. And this is something which could be done faster. Unfortunately, for the exact match, and since fingerprint is a technique of some sort of hashing, you could say, where you try to reduce the actual complexity of the compound to certain, let's say, 2000 bits fingerprints, it still leaves the possibility that different compounds could lead to the same fingerprints. So that's why after this intersection, we still have a need to do this additional exact match after checker, let's say. And this is something we're looking potentially maybe improving in the future releases of this API. Something similar happening in the substructure match, where we once again doing the intersection of the bits and finding those. But once again, I think similarly with the fingerprinting situation, hashing scenario, we need to make sure, you know, that we're not providing the candidates which are not that relevant. But to be honest, I think this was more or less clear even before. And I think where really this API is shining is in a similarity match. And this is because when we're doing a similarity match, instead of having a need to do an intersection, which is relatively quick and probably quick in other storages as well, we would need to do the union here. So we would need to say, hey, my query molecule have bits 1, 3, 5, and 7. What I really want to find is actually all of the unions where at least one of these is findable. And this is, of course, creating potential problem where we have a huge list of the results. And one of the important things which is helping us quite a lot is the ability to have a certain threshold on, let's say, some of the metrics. So if you're talking about Tanimoto metrics, for example, saying for the request that I want only to return compounds which have a Tanimoto similarity matrix above certain thresholds, let's say 0.8, provide us with an ability to create additional logical conditions saying, hey, in order to get those, you need at least, and I'm like completely coming out of without correct calculation in this case, but for example, if I want 0.8, I need at least 2 of those findable. And this is already improving and making the query much, much faster. So let's take a look very briefly maybe to how this API looks like. And I think what we were trying to achieve, I think, is we were looking at some of the, let's say, open source alternatives which are existent in the space. And to be honest, I'm not sure about like our participants' experience, because it could be different, of course. For me, it was always a little bit difficult to find like a set of APIs which would be, let's say, human-friendly or something which I would, you know, will be feeling nice to use or like feeling myself as a, you know, good usage of. So that's what we were trying to do at the very beginning. And this is, for example, you know, how we could just, you know, create the repository and basically connect it to the host of Elasticsearch. Basically, if you could here take a look at the Java version of it, we're using the like builder pattern where basically, hey, I want to connect to my instance and the local host, this port and this scheme, and give me the repository. And I think in Python, of course, which is the king of writing a shorter even code, this looks even more concise and more nice. As I already said, our API support different types of format like SDFs and mol files and smiles files. So we have certain sets of helpers which are basically allowing you to create a stream of records where you could put them into Elasticsearch pretty easily. And this is one of example of how you could do this. Something similar could be done to do an exact match. And here, once again, I think maybe our stream API, in this case, creating the diversion, so it looks like very, very much complicated, and the Python version, to be honest, looks much better. So I don't know if it's really some sort of comparison, and people would lean towards the Python version after all. But yeah, we're still thinking about potentially extracting those exact match after checker later on in order to hide those abstractions for the users of the API. Something similar happening in the similarity match, but once again much more concise. And for the similarity, I didn't talk about this before, but by default we like supporting the Tanimoto one, which is we call it either similarity match or Tanimoto match. We support the Tversky metrics and the Euclid distance as well. So this is something once again you could use, and we're thinking about potential pluggable similarity as well. I think one thing to mention as well is that during previous version of this work with the Solar one, I think what was really important is that even though the ability to do these efficient queries were there quite a long time, the actual need to have a proper metrics embedded into the engine itself was a difficulty. But in our case, we were able to solve this quite efficiently with a Boolean similarity. So basically, instead of working on the term frequency and inverted document frequency, which is usual case for information retrieval agents, we rather were working on exactly how many bits of the fingerprints match, and it's working quite nicely for us. Another obviously a benefit from having those is that our API is completely doesn't require any sorts of additional installation. So this is once again something we are proud of and thinking this is a good use, just because very often in this situation you need to install some different plugins, and sometimes it could be like or extension, you could call them differently, cartridges. Some people call them cartridges as well. And you could think about it, hey, I don't want actually to install anything, or I'm using a cloud provider. So very often when using service at the cloud, some sort of cloud provider, for example, they're not giving you ability to actually install any sorts of plugins. In our case, we don't need any extra, and that's I think one of the advantages of the use of the stuff that we created. And once again, something very similar we have for a substructure match. Still thinking about making this better. And I think very interesting, very cool thing which we did once again, have additional support for custom fields filtering. So for example, here you could see how with the Java version of it, I'm trying to find the most similar molecules by the Tanimoto one, and then I'm also filtering out by the wildcard query on the tag field. So basically I'm trying to find anything which is start with the test, which I have a star after all. And with the Python version, I'm trying to show how it could look like if you have some sort of by activity value of a certain target, and then you have not only the similarity requirements, but also some by activity requirements as well. What is very important to say is that we're still under development. We still only just release, let's say, releasing the first version of it. We still have a lot of stuff to improve ourselves and that we want to do. For example, API for different languages. So I'm really keen to hear if anybody really have a need rather than Java and Python, maybe for different languages, maybe .NET, C#, other stuff. For initial release, we also skipped the tautomer search and cross formula search, but this is something we're gonna add pretty soon. Marketplace integration for major cloud providers. This is something I personally look very much further, because I could imagine it's very convenient to say, hey, let's spin me a cluster of Elasticsearch. I want an API to be pluggable, and then I'm just indexing whole content of the PubChem database, and I'm ready to go. Support for the custom fingerprints, and yeah, as I said, something as a sort of suite of tools, maybe working with the PubChem or Campbell or any other open source, sorry, not open source, but like open data. I think once again, as coming from the engineer and being an engineer myself, it's very important then when you have certain type of problem, I want I want to find, like, let's say, an easy solutions, and that's what was our motivation as well. I have a very simple comparison with like some of things which we may call our competitors, and I don't want to be that much of a comparing and stuff like this, because I think once again it's very important that what we're trying to do is to suit it for the modern NoSQL storages, and it's about the easiness of using the API. But I think when we're looking at the competitors, I personally aware of, let's say, of several open source ones, and I want to make sure that we are talking about open source. We're not talking about proprietary ones. And in this case, let's say OpenBabel and CDK are both having like Python and Java API, but they don't have any sorts of cartridge or plugin in order to store it into some sort of relational database or NoSQL database, for example, which I think is considered to be a not so good library maybe to use. Obviously, there was one of the big players in this field, RDKit. They have a different APIs in Python and Java, and of course they have a PostgreSQL cartridge. So I think comparing to them would be the most interesting one. But this is something I'm rather don't want to start some sort of holy war. So it's probably I want to work later on in order to compare exact numbers and, let's say, compares different functionality. So yeah, conclusion, I think, more or less, coming to the conclusion. I think once again, Java Python based API, storing this into Elasticsearch. As I said and probably mentioned, this is completely open source. We don't want to get any sorts of profit, and I personally myself a very big open source fan and an open source contributor, which I think is always helping. And I think maybe life science or let's say drug discovery field, at least personally, looks to me like a less open to the open source, and for obvious reasons, of course. But still, this is something I personally like quite a lot. And during the talk, I was using quite often the word "we," and because this is not just work was done by myself, but by a number of my team members, my colleagues, who are helping me both with like this implementation and understanding cheminformatics and chemical reality. Let's say these similarity matches, because I must admit that's pretty difficult and pretty hard, and it's still pretty hard. I'm still learning quite a lot. And just a small topic of Notion. I mean, we don't have only just this Elastic API. We have any different sorts of open source products which exist there, and this is just name of a couple of them. We have a web-based chemical structure editor. We are working on optical recognition of 2D chemical structure images. This is, I personally want to contribute quite a lot in the forthcoming months, especially looking into how, let's say, deep learning techniques could help us to do the better job here. And we have even more, of course, different other aspects here. Here are just different links that I've used during my my work here, and yeah, the first one is the project that was talking about, the Indigo one, and there is of course some reference for the Elasticsearch documentation, fingerprints, RDKit, and stuff like this. So yeah, thank you very much for listening. So yeah, let's have a questions.
Great, thanks a lot, Konstantin. It's quite but if you're free to send me the slides, by the way, if they are open, I can put them on the website because of the links and so on, so people have those. And it's quite a small community, by the way. There's Raj, for example, he was involved with RDKit here as well, and so on. And feel free, I mean, if you want to talk to people in the field, get in touch and have a talk with the people directly. I think that might be beneficial as well. Or get in touch with Konstantin the other way around, of course. Yeah. There were a few questions. Pierre Ducrot, yeah, he wants to ask about tautomers. Pierre. Otherwise, I can read the question in case.
I was just the time to find the unmute button. Actually, you answered the question at the end. It's you are going to look at the tautomers in the future, but really, as you're using fingerprint, I was wondering if you had look at how your searching performs with tautomers.
Right, but sorry, that's what I said, right? So you don't have a support for tautomer at the moment yet. So it would be honest to say that you don't have yet a comparison with it, unfortunately.
Yeah.
Yeah, this is one of the tricky topics. Yeah. That's right. Okay, thank you. Thanks, Pierre. And Bola has a question regarding the fingerprints. Could you ask the question, Bola?
Yes. Can you hear me?
Yeah.
Yeah. So thank you first for your interesting talk. It was really nice to hear it. And I have some chemistry-oriented questions, if you don't mind. The first question is, what kind of fingerprints have you been using to encode your compounds? And since the search is, as you said, it's fully textual, does it account for the 3D information of the structures or not, if they are stereoisomers or something enantiomers like this?
I need to open my disclaimer on the Cheminformatics 101.
Yeah, that's why I said from in the beginning it's chemistry-oriented questions, so it's okay if you.
So yeah, I think it's fair to say that we're using so basically there is this open source library, the Indigo one, which having some sort of special their own fingerprints. I think if it's probably the right assumption. So we using those, and this is I think why one of the things we really want to take a look at here. This is a slide, right? We potentially, not potentially, but like we heavily looking into potentially plugging different fingerprints and fingerprints types, of course, because this is like, I think the main idea is that you have ability to search based on the fingerprint, but then of course fingerprints are different and they could have a different of properties. It's basically some sort of hashing technique, at least once again, to me, how it looks like, right? Because you're going from this difficult stereochemistry, even potentially a structure, into something which looks like, zeros and ones, right? And a supporting for the fingerprints, I think it should be very important, and it will be very important for us. But at the moment, we're using the standard one, which are available. I think it's. Let me take a look what kind of fingerprints it is. So I think it's. I don't want to lie, to be honest.
Okay. Can I ask another very quick question?
Of course, of course.
If you have two substructures which are feature-wise similar but not really the same substructures, will they be considered similar or not similar? Like as I mentioned in the chat, if you have something like OH, SH, NH2, they are similar when it comes to feature-wise or pharmacophoric point of view, but will they be considered similar in your search or not?
Let's take a look like at this kind of slide, right? When I was given the very naive, of course, example of substructure, right? So is it right that you're saying, let's say that instead of HO here, for example, I would have something similar but SH group, let's say, or
yes, but I mean in this example, the rest of the compound is still the same as the rest of the compound on the left. So both of them are the same. So this is not what I mean. What I mean is that if they are not the same as text, as atoms, but yet they are the same feature-wise or functional-wise.
No, I think then it wouldn't be considered the same, right? Because I think the idea of the substructure, and at least to me, once again, I apologize for my naive understanding of cheminformatics, is that as long as you have in those graph representations, you have similar types of nodes, let's say a benzol ring or similar structure of it, and maybe even the rest of it is completely different, this is still will be considered as a substructure match. I'm looking at Andreas.
It depends on what precisely you do, basically. Yeah. Yeah. It depends on how you type atoms and how you define things. It really depends. Okay. Yeah. Maybe let's. Yeah. I'm not quite sure. Yeah. Let's maybe move on to the next question. Yeah. Thanks, Bola.
Sorry. Just for a short one. We could try to do like a live demo in a breakout room or something, just looking at the different examples and see if they actually matching or not. If it would help. I'm happy to do this kind of stuff because once again, it's engineering. So,
It's fine. I can put Bola into your room. I think that should work. I will try to do that. Yeah, thanks.
Okay, perfect. Thank you.
And we had a comment from Raj as well, because he was involved with the RDKit and CDK, I think, at some stage. Raj, because he mentioned, and John also mentioned, which database interfaces there are and so on. Raj.
Yeah, so I have been associated with the CDK really in the past, and just wanted to note that it has been integrated into some databases, Oracle and Postgres specifically.
Thanks a lot for this. I mean, at least when I was doing my research, I wasn't able to find this, so I'm not sure if it's me not able to find this properly, or maybe it's not mentioned like on the main CDK, let's say like documentation page or something. So thanks, definitely thanks for those links. I will definitely would need to update those to make sure it's there. So yeah, thanks.
Yeah. Feel free to talk to the people directly. You can remind me afterwards in case you need any particular information, because it's, as I said, it's quite a close community. Egon Willighagen, you might want to talk to as well. These are people who are co-contributors for those things. Yeah, they can give you any detail you might want to have. Yeah.
Absolutely.
Yeah, John mentioned some information as well. Is there anything you would like to add here, or because it was more factual, John?
Yeah, I think it's just basically about the same. So that's my mistake. That basically OpenBabel have some sort of cartridges as well, which is once again I'm really not like doubtful. I'm just worried like where this information is hidden because I wasn't able to find it. So and I'm even looking at the moment right now with the CDK page. Once again, there is no mentioning of it at all. Maybe they should put it over there, of course.
Yeah, our advertising is not as good as it should be.
Yeah, and documentation, all that. That's a different. Feel free to follow up afterwards with John and Rajashi and so on. Yeah, absolutely. Yeah. Okay. And yeah, you were thanking John already. And Maria had a comment, or a comment as well. Thank you for the presentation. She has been working with MongoDB as well. Maria, is there anything you would like to add regarding your comment?
Not really. Apart from that, I'm really happy that there is now some chemical work on Elasticsearch, because Elasticsearch is way more powerful for actually searching data rather than MongoDB. A couple of months ago, there was a presentation from Google Summer Code that was joining RDKit with MongoDB, and that was pretty nice, and it was pretty cool to observe. And as Elasticsearch it's pretty similar in the storage way to MongoDB, it might be worth looking into it. But yeah, thank you again for the presentation. It was nice.
Thank you, Maria.
Okay, excellent. Are there any other? Oh yeah, Daniel. Daniel has a question as well.
I was just wondering whether you compared the performance with the other implementations of Bingo, because there's an existing cartridge for Postgres and there's also a NoSQL version of Bingo. Have you done any comparisons with the performance of those implementations of Bingo?
So yeah, of course, since it's under umbrella of Bingo or Indigo, of course, we did some of the comparisons with NoSQL directly. Once again, just because Elasticsearch is heavily a NoSQL database or storage, you could say. So that's why we compared with NoSQL. And I think for them, I think we went faster in terms of like indexing the data rather than NoSQL. So I think we did it faster. I think NoSQL was a little bit faster on the retrieval. But once again, this is a little bit unfair comparison, especially because what we're trying to show, we don't want to say, let's say, that our cartridge is the best cartridge or our API is the best API, right? We're trying to extend the applicability of Cheminformatics to different storages, first of all. And second, we're thinking like that the features of additional filtering, especially full text search range filtering, this is something which stood up quite a lot and makes these a little bit different from others. So yeah. I don't know. It's not really an answer, but I think once again, it's on our plans as well to have a more comprehensive performance comparison, either with inside the Bingo or outside of it. But once again, I don't know. Once again, this is, as Andreas keeps saying, this is a very close community. I don't know how much people or public will be very interested in this kind of stuff, right? Like having a complete performance benchmarks of different sets of tools. I don't know if it could create, let's say, maybe a tension between like, because I mean, once again, at the end, of course, I could imagine some people are more focused on, let's say, one of the implementation over the other, just because they may be used to it. Maybe they see these features as more important, and having those performance, will it be, you know, creating a diversion? I'm not sure. You tell me. Yeah, that's what.
No, I don't think so. I think in the field, it's not really competition as such. It's, I mean, it's a close community, yeah. So a close in the sense of people know each other well, yeah. It's not close to others, so everyone's welcome, basically, yeah. But it's more about, well, finding a way to have open toolkits, yeah, that do what you want to do, yeah. It's valuable information, yeah. And then, I mean, if you know what works better, everyone knows that, and the field can develop, yeah. I think, well, it's my personal viewpoint, but no, it's a very nice community, actually. I would encourage you, Konstantin, to talk to the people. I can bring you in touch with the people you were talking to here. Might be good people to follow up afterwards with, basically. Yeah. Basically, to advance the whole field, yeah, that's the idea of that, yeah.
Thank you.
Yeah.
Thank you.
Yeah, there's also a benchmark. John was just sending a link that might be valuable to have a look at. Benchmark from previous Cheminformatics meeting. Yeah, it's in the chat.
Yeah, absolutely. Thanks, John. It's very good. I mean, ideally, looking at the different cartridges, and once again, thanks for all the people who send in those different ones. Potentially, it could be very, very interesting project to compare, you know, different sets of those. So yeah.
Yeah,
cool
so valuable information to have. Yeah, yeah, yeah. And you see, there's a volunteer already. Maria is very happy to help with benchmarking as well. You see, it's all coming together now. Yeah.
Yeah, that's good. No, that's good. That's what I like to hear. I mean, I don't know. At least that's what I'm not making any sorts of judgments or something, but that's at least what I was even being told a little bit. So don't, you know, what's the word? I'm not sure what's the word. Is like create some sort of diversion and say, hey, you know, we are better, we are faster than X, because and then what people say, hey, you know, we're using this technology for a lot, for a while. Don't say, you know, crude words like this. So yeah.
No, but if something is faster, it's a contribution to the field, right? It advances the whole field. I mean, that's another way to see that, right? And there's nothing wrong with that usually.
Yeah, that's once again why I'm feeling personally. It's very good having those being open source and being, you know, available to any scientist, any practitioner to try, because this personally to me is driving it further, and we could improve and could make it all make it better.
No, that's right. Okay. Is there any final comment or question for Konstantin? Okay, yeah, then thanks a lot, Konstantin, and thanks to both of the speakers. Please stay on, as I said, so now comes the pub night, so to speak. So our next meeting will be on the 10th of February. Please join us. Please let me know if you would like to present in particular, if you have information to circulate. And please stay online. It takes about a minute or so until you're in the breakout room. So I will put clusters of people together, so to speak, so no one stays alone. So thanks a lot, everyone, for joining, to the presenters in particular, and have a good night. And have fun at the pub night right now as well. Thank you.